Hello guys, yet another video. Today we're gonna be looking at a new problem, and same we're gonna go through the problem, read the problem, discuss the complexity and how it works, and then we write code for it. So our problem for today is find closest value in BST. Write a function that takes in a binary search tree, a target integer value, and returns the closest value to that target value contained in the BST. You can assume that there will be only one closest value. Each BST node has an integer value, a left node, a right node. A node is said to be valid BST node if and only if it satisfies the BST property. Its value is strictly greater than the values of every node to its left, and its value is less than or equal to values of every node to its right. And the children nodes are either valid BST themselves or none. Okay, so let's dive into the problem. We open the whiteboard and we'll look into this. Now, first of all, let's discuss what the binary tree is, right? You can think of binary tree as a tree that has subchildren, right? And it's always divided into two subchildren. Binary because 1, 0, right? So two, always gonna have two children, okay? That's your binary tree. Now, any structure like this will be your binary tree, which has always two children, can have max of two children, right? So this is your binary tree. Now, what's a BST, right? So let's see what a BST is. BST is anything that's satisfied as a property, which says that the left node should always be smaller than the right node. So if this is 5, left can only be 4, which is smaller than, and right can be either equal to the root node or, greater than the root node. So it can be 6, or the right can be 5 itself. Sorry, 6 here, right? Mm, Oh no, I think it's one mistake. So can be 6 itself. It can never be, anything else. The left one would always be smaller than the root, and the right one will always be the greater or equal to the value of the root. And anything stored inside is the value. So here the value is 5, value is 4, 6, 6. Right? Now it says in the problem that, let me erase this. So problem says find the closest value in a BST. So the example BST that's given is number 10, 5, 15, right? 2, 5, and then 13, 22, 13, 22, and 1. This one is what? 14, right? So closest value will be closest to what? Closest to what? The target that's given. So here in this case, target is given to us as 12, right? This is given, so don't have to worry. Now, when the target is run, the closest value, find the closest value in BST. So if you compare, first we're going to compare all the nodes with number 12, okay? So the difference between 12 and 10 is what? The difference between both the values here is 2, right? Closest value because it's asking for, right? And the difference between this one is 7, 12 minus 5. Here the difference is 3. Here difference is what? 10. Here difference is what? 7 again. Here difference is what? 11. Here difference between 12 and 13 is what? 1. Right? Here difference between 12 and 22 is what? 10. 12 and 14 difference is 2. right? The difference here is 2. So it says find the closest value, the one that's closest to the target. So which one is closest to the target? So closest would be whichever wherever the difference is the smallest is going to be the closest, right? So here 2, this is small. 2 is smaller than 3, okay. And here 1. 1 is like smaller than 2. So 13 is the closest value to that particular, to the target. Right. Now there's one more thing. Since it's a BST, we can do one more thing. We can see, okay, 12 is our target. Is we also know the BST property, right? BST property, what does it say? Left ones are always going to be smaller. The right ones are going to be equal or greater. So is 12 greater than 10? Yes, it is. So you can come here, right? Okay. Is now with 15, is 12 greater than 15? No, it's not. Not even equal to. It's a smaller. So come here, right? Is 12 smaller than 13, right? But here there's no node. This is empty. So we don't have to worry, right? So we don't have to calculate the difference with each node. We just have to calculate the difference at this node, right? And this node, right? Following the property of BST. If we just calculate the difference between these three nodes, it will tell us which is the closest value to the target as per the property of BST. Now, in BST, when we do this, what would be our complexity, right? So let's just say, what is the complexity in this case? So in this case, right, our complexity would go to what? Let me see. One time, I'm gonna the worst case scenario is going to be O of n, right? Because I'm visiting every node once, right? But let me see, let me just make sure. And the average case scenario, right, would be O log of n. This is my worst case scenario. O log of n would be my best case scenario when I don't visit all the nodes because I'll be visiting one, two, three, all three, only three nodes, right? Or in a different, tree, I could be visiting more. But at the worst case scenario, I'll be visiting all the nodes once, or I will visit O of log n nodes once. Now, the space complexity for this kind of a program, right? Let's see what we're going to do. Are we going to be now? Okay, let's talk about traversal for that, right? Let me copy the diagram once again. So our tree was 10, 5, 15, 2, 5, 13, 22, 14. So there are two primary ways of traversal in a tree. You can call them BFS and DFS, right? But tree traversal usually happens in three ways, which is called in-order traversal, pre-order traversal, and post-order traversal. Okay, we'll see these all in future examples. I don't want to complicate this particular problem. Right now you can just think of, you can either use BFS or DFS. DFS, always remember you use stack, and BFS you always use queue, right? To traverse over this one, what can I do? Now, I can take route 10 in the queue. I take 10. Okay, go to 10. Now see, 10 has children, right? But as per the BST property, my target is 12, so I'll go to the right. I don't need to go to the left. So I will only store, when I am visiting 10, I will store 15 here, right? That is the only child I care about. Then in case of when I visit 15, when I pop 15, what I'm going to do is look at their left and right child. But I only care about the left one. I don't care about the right one since the number is smaller. I put 13 here, right? And when I take 13 out, when I take 10 out, I'm going to calculate the difference and tell you that, out of these three, the lowest difference 13 has, which is like 1, because this has 2 and this has, I think this also has 2. So the lowest difference here is going to be the 13th, and you print out the 13th value, right? So you got the, if I use Q, now it can be done with and without using Q. If you use Q, your space complexity will be O of n, or you can say O of log n, but O of log n, no, because you're storing all the nodes, right? So it has to be O of n. I'm so sorry for that, my mistake. Yeah, your complexity here would go O of n. And if you don't use Q, your complexity will go O of 1. For simpler purposes, not complicating the problems, and it's the first BST problem, we'll use a cube, right? To keep it simple. Now let's look at the example. Let's go and write the example. Okay. So this is the sample tree that I showed you, right? I've created the tree and I've called the method here, and I have a class BST just to store that, custom BST. So what I'm gonna do is I'm gonna take the tree and the target, right? Let me check. Okay. Let me see what I need to do here. So let's start coding. Okay, let's just say first we have a queue, right? So I create a queue. Now my data type is going to be what? Tree type. And I do data is equal to new linked list, right? And then, like I said, I'm going to add my first tree to this one. So I will just say add. My first BST is what tree? So I put it here. Now what I'm going to do is while, I'm going to take a while loop. While my, let's just make it here. Okay. While my queue is not empty, this is empty, right? So I'm going to make it not empty. While my queue is not empty, what you do is you take a BST temp b equal to queue dot pop. No, sorry. So you take up the first what I did is I entered the root inside my queue. That's my root, right? And now what I'm doing is every time I take the root out and I see if it has children. Now I'll check. Okay, if so target is say greater than tmp dot value. If target is greater than the value, right? Then greater than or equal to, right? Oh, I'm sorry. So if target is greater than, no, equal to, if it's equal, let me see. Just want to do equal. Just, okay, that's fine. Doesn't matter. If target is equal to temp dot value, if it's greater or equal to, then what you do is you go temp. Okay, temp is my root. Now root, if my target is greater than the root and temp dot right is not equal to null, right? If it's not equal to null, then what you do is you go to right. So you do tmp dot Then you go to right. Then you do go to right. So for that you will add q dot add this one. And there's another is going to be if my target is less than p dot value. So this is my left, right? If it's less and tmp dot left is not equal to null, then you do what? You take add it to the queue. Add BST, add it to the queue. Now I also need to check the difference, right? So let's check the difference, right? So my dot absolute value of my difference between my target and what else? Difference between the target and the temp dot value, right? Temp dot value. Now I'm gonna put math dot absolute with these because I just want to make sure that values can also be negative, so I just want to make sure that it gives me the right difference. Math dot abs absolute value. So I get this is how I get the difference between the two, right? Now once I have the difference between the two, I'm gonna do one more thing, right? I'm gonna create one more variable, which is my, let's just say the IFF, right? And I'm gonna say this is equal to integer dot max value. And here I come and I say if my diff, right, is less than, no, diff is supposed to be less than, right? Okay, if diff is less than, no, sorry, if difference is less than diff, then what you do is you do diff is equal to difference. Okay, and also I'm going to do one more thing here. I'm going to do int node is equal to -1 for now. Let's just keep it 0. So in this one, every time my difference is smaller, I'm gonna add here, store my node is equal to temp dot value at that particular node. I will store it so that later I don't have to find in my queue, or later I don't have to worry about which was the closest node. So I'll just store the value as you find a difference, a smaller difference, right? Anytime you find it, just store that value from the node so I know which node it was. Anytime the difference is smaller. So I get temp dot value node, right? Node, I store that value. Now I just have to, here I'm going to do if if root, right? Not root, let's just say tree. If tree is not equal to null, then what you do, okay, if tree is not equal to null, then you return node, else just return -1. Okay, let me take this one off. Okay, now let's run this program and see what happens. I hope I didn't make any mistakes. Mhm. Ouch. So now you see my target value here I've set as 13. Let me make it 12. Now you see 13th node, node number 13 has the smallest difference. And one more thing, this is the linear approach of solving the problem. Okay, you can also use a recursive approach, but linear, no, not sorry, there are two approaches, iterative and recursive, right? This is the iterative approach and not the recursive approach. You can also solve the problem using the recursive approach, but when anytime you have two different approaches, say recursive and iterative, what is it called? Iterative, right? Just check, I could be wrong. Recursive and iterative, something else called. So iterative approach is always a better approach than recursive. Always remember that because recursive stores call stack and iterative does not. Okay, so it's always going to be a better approach. So this is your solution, and you can see we are only using the while loop once. So at max, it goes over all the nodes, which is O of n and O of log n, if because it's not going to go over all the nodes. It will check, left and right, which one is smaller, and then decides. And we have used a queue. So O of n space complexity, you can also avoid doing that. That's going to be your answer solution. All right. Thank you so much, guys, for watching this video. I'll see you in the next one with a new problem.